Hi everyone, due to some technical difficulties, this is going to be part 2 of our diagonalization video. So recall the question at the end of the previous video was wanting to know whether or not this matrix is diagonalizable. And remember, we know that a matrix is diagonalizable whenever there is a basis of Rn, in this case R3, consisting entirely of eigenvectors of this matrix A. So you say, well, we need to go and fetch bases of eigenspaces, right? You're right. So how do we do that? We first need to find the eigenvalues. So let's find the eigenvalues. We know that we need to compute determinant of A minus lambda I. And the determinant of A minus lambda I is, of course, the determinant of the matrix 2 minus lambda, negative 2, negative 2, 3, negative 3 minus lambda, negative 2, 2, negative 2, negative 2 minus lambda. Yeah. Whenever you take the determinant of this is of course called your characteristic polynomial, and the roots of this characteristic polynomial give you your eigenvalues. And whenever you find the roots, of course you set it equals 0, yeah? By a little bit of magic, you'll see that the eigenvalues are 0, negative 1, negative 2. And in this case, because the eigenvalues are distinct, we know that we will have a diagonalizable matrix. Yeah, because each of the eigenspaces will have dimension 1. And the sum of all three of those dimensions is 3, which is the dimension of the original matrix. So, how do we diagonalize the matrix now? Let's go and try to find a basis of each eigenspace. Remember that we now know that it is diagonalizable, so it does admit a similarity transformation of the form A equals V dV inverse. V is going to be, as we showed, the matrix of our eigenvectors. Yeah, you pick your basis for each eigenspace, you throw those in the columns of V, and D is going to have be a diagonal matrix with only the eigenvalues along the diagonal. So we have our three eigenvalues, 0, negative 1, negative 2. We know what D is, right? What's D? D has to be the matrix 0, 0, 0, 0, negative 1, 0, 0, 0, negative 2. Yeah? We could actually reorder the diagonal, but now that we fixed the ordering of D, the ordering of V is fixed, it turns out. The first column of the matrix V will be whatever basis of the eigenspace for lambda equals 0. The second column will be a basis for the eigenspace corresponding to lambda equals negative 1. Here's my cat. I'm going to pause and try to get her out. Sorry about that. And column 3 of V will be a basis vector corresponding to for the eigenspace corresponding to lambda equals negative 2. So for lambda equals 0, how do we find a basis for this eigenspace? We of course want to find a basis for the null space of A minus 0 I, right? So that's just a basis for the matrix, for the null space of the original matrix. Yeah. So how do we find a basis for this null space? We do some row operations, and here I'll suppress this because I hope that we're all experts and totally bored with finding bases of null spaces. But if this is mysterious, please, please, please reach out and we can talk about this and we can go over this step by step, I promise. And I think the row echelon form is 1, negative 1, negative 1, augment 0, 0, 0, 1, 0, 0, 0, 0, 0, and be sure you're okay with this computation. Like I said, if there's something at all mysterious here, just let me know and we can talk about it. Well, let's find a basis for the solution set here. I know that x3 has to be 0. I know that x2 is a free variable. There's no pivot in the second column, so let's call it t. And I know that x1 is going to be equal to t as well whenever we solve. Yeah? And so what's a basis for the eigenspace? E sub 0, right? Lambda equals 0? It's just the set with the single vector 1, 1, 0. Okay. All right. Let's find a basis for the eigenspace corresponding to lambda equals 1. or negative 1 rather. Whenever we compute a minus 1 times the identity, I think we get 3, negative 2, negative 2, 3, negative 2, negative 2, 2, negative 2, negative 1, augment 0, 0, 0. And how do we find a basis for this null space, or for this, the solution set for this equation? We do row reduction again. And again, if there's any mystery here, please let me know. So whenever we perform a little bit of magic, there's my cat, we should get 1, 0, negative 1, 0, negative 2, 1, 0, 0, 0. She thinks it's nap time. Augment 0, 0, 0. No kitty. Come on. All right. So how do we find a basis for the solution set? I know that I have a free variable here as x3 because I have my pivots in the first and second columns. So x3 is free. What's x2 have to be? x2 looks like it needs to be 1/2 t, and x1 has to be t. And so now what's a basis for this eigenspace? Looks like it's going to be the set 1, 1/2, 1. Yeah? Or if you prefer, you could scale this basis vector, if you don't like the fraction, right? You could scale it by 2 and you could get another basis vector. Remember, bases are highly not unique. So you could also have 2, 1, 2 if you prefer. Yeah? Another good basis for this eigenspace. Oh, and this is the eigenspace corresponding to lambda equals negative 1. Now, one more. Let's find an eigenspace, or sorry, a basis for the eigenspace corresponding to lambda equals negative 2. If lambda equals negative 2, a minus negative 2 times I is going to be 4, negative 2, negative 2, 3, negative 1, negative 2, 2, negative 2, 0, I think. Augment 0, 0, 0. Perform your row reduction magic. We see that the row echelon form here is 1, 0, negative 1, 0, 1, negative 1, 0, 0, 0, augment 0, 0, 0. And now I see that I have pivots in the first and second column again, so x3 is 3, x2 has to be t, x1 also has to be t by solving these equations, and a basis for this eigenspace is the set with just the vector 1, 1, 1. Yeah. So we see that we know that we were diagonalizable because we had 3 distinct eigenvalues, right? And here we have 3 different eigenspaces. Each of the eigenspaces have dimension 1. The sum of the eigenspaces is 3, which is the dimension of the matrix. So again, we know that this is a diagonalizable matrix. And what do we know now immediately? What's a basis for R3 consisting entirely of eigenvectors for A? It's just the set with these 3 vectors thrown into it. 1, 1, 0, 2, 1, 2, 1, 1, 1. Yeah, and this is now a basis for R3 consisting entirely of eigenvectors of the matrix A. And that's kind of interesting. So with this, we have everything that we need to diagonalize our matrix. So let's do it. I now know that A will be equal to the product of 3 matrices, right? I'm going to be lazy. I know this will be V, here's D, and here is V inverse. Yeah, and I'm just going to put V again here and I'll compute the inverse. And I'm not gonna actually compute it. I'm gonna be lazy and leave it as matrix inverse because I know that we all know how to compute the inverse of a 3 by 3 matrix. So what was our matrix D? Matrix D was 0, 0, 0, 0, negative 1, 0, 0, 0, negative 2. And remember, once we fixed the order of the eigenvalues on the diagonal, the order of the eigenvectors of the bases of each corresponding eigenspace are fixed. So what goes in the first column is the basis for the eigenspace corresponding to lambda equals 0, which was 1, 1, 0. The next column is the basis for the eigenspace corresponding to lambda equals negative 1, which we called 2, 1, 2, I think. And the third column of V is the basis for the eigenspace corresponding to lambda equals negative 2, which is 1, 1, 1. And now I just copy that here, 1, 1, 0, 2, 1, 2, 1, 1, 1. Yeah? And that's not so bad. What happens if you were to swap? What if you were D, instead, let me put it in red, hypothetical red here. What happens instead if your D matrix, you really want it to be negative 1, negative 2, 0, and 0 is elsewhere? What would you do? What would your V matrix be? Well, it's going to be the first column has to be the eigenvector. That's a basis for the eigenspace corresponding to lambda equals negative 1, which was 2, 1, 2. Then comes negative 2, which was 1, 1, 1. And then comes 0, which is 1, 1, 0. Yeah? And whatever that is, you just compute V inverse over here. So again, once you put the order of the eigenvalues in D, the order of the eigenvectors is kind of fixed. All right. Let's talk about who cares, right? Who cares about this diagonalization? First, if we have that A is equal to V dV inverse, and remember, D is a matrix with the eigenvalues along the diagonal, right? Repeated according to their multiplicity. Repeated according to multiplicity. So, what do we know? We know that the determinant of A, how can we compute the determinant of A? It's the determinant of V dV inverse. But as we've seen in the previous video, the determinant of V times the determinant of V inverse multiplied to give 1. So this is just the determinant of that diagonal matrix D. And what's the determinant here? It's just the product of the eigenvalues. So this gives another proof that if you have a diagonalizable matrix, right? If you have that, then the determinant of A must be the product of the eigenvalues. What if A is invertible? What if we know that A is invertible? How can we, and we know that it has this presentation, V dV inverse. How can we compute A inverse? Well, it's going to be V dV inverse. And as we recall from earlier in the course, how do we take the inverse of a product of a bunch of matrices? The order flips, and everything gets an inverse, right? So this is going to be this matrix, V inverse, but with an inverse, times the next matrix, D, with an inverse, times V, with an inverse. What's V inverse inverse? That's just V. So we have V, D inverse, V inverse. So we get something for free. If A is invertible and diagonalizable, the inverse is also diagonalizable, and we immediately have the diagonalization. We already know the eigenvectors, yeah? And what are the corresponding eigenvalues for A inverse? It's just the reciprocals of the eigenvalues for A. And keep in mind that there's no problem here because the diagonals have to be non-zero, right? Because if you're diagonalizable, or sorry, if you're invertible, none of your eigenvalues can be 0. So D inverse is well defined. All right. Let's talk about something else. Suppose again we have that A is V dV inverse. How would you compute A squared? It's just A times A, right? So that's A times V dV inverse times V dV inverse. So A squared is just V dV inverse times V dV inverse. What do you notice happens to these two middle V inverse times V? They multiply to give 1, right? So this is just V times D, or sorry, that's the identity matrix, times D times V inverse, which is just V D squared V inverse. And this is kind of cool. In general, what's A to the K going to be? All the interior V inverse times V's will cancel, and we'll be left with V D to the K V inverse. And this is super nice. If you have a 1 million by 1 million matrix, how would you raise it to the 100th power? It's terrible, right? But if you have its diagonalization, raising a large matrix to a large power is simply raising the diagonal elements to a power and then multiplying it by V and V inverse. Yeah? So this is computationally, if we can get a computational way to quickly and efficiently compute the diagonalization, raising matrices to large powers is very, very easy. Yeah? And let's just make sure that we're okay with that. If our matrix D is lambda 1 through lambda n, I'll put it up here. What is D to the K? It's just all of the and zeros elsewhere. It's just the diagonal entries raised to the kth power. And that's super easy to exponentiate. Yeah? So because it's related to these nice diagonal matrices, anytime that we want to exponentiate matrices, this diagonalization is really, really, really useful. Yeah? And if A is invertible, then this property here is true for any k that's an integer. Any k that's an integer. Alright guys, so I think that does it for this video. I hope that it helps. If you have any questions whatsoever, please don't hesitate to reach out via email, and I'm happy to help with any way that I can. Or we can set up a time to chat in Zoom and go over any problems that you're having. And I look forward to seeing you in the next video. Thanks so much.